Welcome to lesson 18 of complex analysis. In this lesson, I'll talk about complex sequences, some tests for testing convergence or divergence of a sequence. We'll talk about complex series and then several examples throughout the lesson will be provided. Okay, let's look at a couple of examples. As a first example, we'll take the sequence I squared, I cubed, I to the fourth, and so on. So we get I for the first term, I squared is minus 1, then minus I, 1, I to the fifth is I, and then you have the series going on, repeating those four terms. So it's pretty much a divergent series. We'll formalize the definition of convergence in the next slide, but I think it's kind of obvious to see here this is not converging to any one value. Now for a second example, we'll take 1 over 2i and the powers of that. So it's squared, cubed to the fourth. We can write that out. We get this sequence here. You get 1 over 2i, then minus 1 over 2 squared, minus 1 over 2 cubed over I, then 1 over 2 to the fourth. And the I minus 1, minus I, and 1, that part of the sequence repeats, but then you have this power of 2 that gets smaller and smaller. So even though you have some alternation in terms, the values get smaller and smaller. So this appears to converge to 0, which it does, and we'll, as I say, we'll formalize this in the next slide. So let's define convergence of a sequence. We have a sequence of complex numbers a sub n going from n equals 1 to infinity is said to converge to a if for every epsilon greater than 0 there exists an n such that the distance between a and a sub n is less than epsilon for every n greater than your capital N. So in that case, we write the limit as n approaches infinity of a sub n equals a. The idea is that the a and your a sub n gets closer and closer as n gets bigger and bigger. And you can make these two as close as you like by selecting your epsilon. So let's apply this to our second example from the previous slide. We take the modulus of our supposed value for the convergence, 0, and subtract from it your a sub n term. This modulus equals 1 over 2 to the n. Remember, the modulus of I is just 1. And that's less than e, less than epsilon, whenever 2 to the n is greater than 1 over epsilon. We can take the log base 2 of both sides of this inequality here. So we get n log base 2 of 2 is greater than log base 2 of 1 over e, which equals 1 minus 1 times the log 2 of e of epsilon. Excuse me. So on the left, log base 2 of 2 is 1. So we get an n there. And so we have n greater than minus log base 2 of epsilon. And whenever that's true, then whenever n is bigger than this, then we have this inequality holding. And we can take a particular example. We can choose epsilon equal 0.001, and we choose our n to be the next integer bigger than the log base 2 of epsilon. So the log base 2 of 0.001 is 9.966, so we choose n to be 10, and whenever your small n is bigger than 10, then your difference between 0 and your sequence term is less than 0.001. And of course, you can make epsilon as small as you want. You just choose your n to be the next integer bigger than this number here, minus log base 2 of epsilon. So complex series are defined in terms of sequences, we define this S sub n just being the partial sum of the first n terms in an infinite series. And we say that if the limit as n approaches infinity of the partial sums approaches or equals to S, then the series is said to converge to S. And then we have this theorem that if a series converges, then the limit of the terms of the series have to go to 0. We'll use this a few times. Occasionally we'll use it in reverse. In other words, if the limit of a sub j as j goes to infinity does not equal 0, then that implies the series diverges. So we'll actually use that more often than in the forward direction and in the following rest of the lesson. So the proof is you let S sub n equal the partial sum, as we defined up here, and then note that A sub n is just the difference between the first n terms minus the sum of the first n minus 1 terms. And since we're told that this converges, our series converges, we have that the limit as n goes to infinity of S sub n equals S, but that's the same as taking the limit as n goes to infinity of n minus 1, S sub n minus 1. And then we just take the limit of a here, limit of a sub n as n goes to infinity is the limit of these two terms, or the difference of these terms. Then you break that into two separate limits, but as we just said, each one of these has a limit of s, and so the value is 0, which is what we wanted to prove. We have a convergence theorem here that's similar to the geometric series for real valued series. You notice here we have the sum from j equals 0 to infinity of a to the j, but now a is a complex number, and it converges to 1 over 1 minus a if the modulus of a is less than 1. Now, in the case of real valued series, it looks almost exactly the same, except you're taking the absolute value of a rather than the modulus. Other than that, it reads almost the same. And in the case where the modulus is greater than or equal to 1, the series diverges. So we can prove this. We multiply 1 minus a times our partial sum here, the first n terms, then we expand it out. And then we see there's cancellation, except for the 1 and the a to the n plus 1, the a and the a squared, and the a squared cancel out all the way up to n, a to the n and a to the n. So we get this equals this, and then we can subtract or add, add this to the other side, and then divide by 1 minus a. And you get this here. And I've just rewritten the this partial sum here this way. You'll see why I did that in a minute, but because I want to take the limit as n goes to infinity. But you have this expression here. Then you take the limit as n goes to infinity of this. You can factor out an a over 1 minus a. And then you just have the limit as n goes to infinity of a to the n. And I claim that's equal to 0. We can prove that by the definition of the sequence convergence. So for any epsilon greater than 0, the modulus of a to the n minus 0, which equals a to the modulus of a to the n, is less than epsilon whenever n is bigger than this number here. So this is our delta. And the question is, how did I come up with this delta? Well, what I did is I took our inequality here. I took the natural log on both sides of this. So you get n natural log of the modulus of a is less than the natural log of epsilon. And that's true whenever n is bigger than this. And notice that we changed the sign of the inequality going from here to here. And that's because the a, the modulus of a, we assumed was less than 1. And so the log of a natural log of a number less than 1 is negative. And when you divide or multiply an inequality by a negative, you change the direction. That's why I got this here. Now, I could have gone an easier route because we had our initial theorem 133, and since we're told that the series converges, then the theorem tells us that the terms, the a to the j, have to go to 0. And so we could have appealed to theorem 133 directly to say that this equals 0. So long story, but the proof of the case where the modulus of a is less than 1 is complete. On the next slide, we'll look at the case where the modulus is greater than or equal to 1. So just tying together the loose ends from the first part of our theorem, we had shown that a to the n plus 1 over 1 minus a equals 0, but a to the n plus 1 over 1 minus a equals this inside here, so therefore the limit as n goes to infinity of this equals 0. And that means that 1 over 1 minus a must equal the infinite sum here where n goes to infinity of this infinite series here, which is what we wanted to prove. The second part of the proof is a bit easier. If the modulus of a is greater than or equal to 1, then the modulus of a to the j is also going to be greater than 1, in which case the a to the j power cannot approach 0 as j approaches infinity. And then we have, by contradicting theorem 133, the series a to the j cannot converge if the modulus of a is greater than or equal to 1. So as an example, let's take the series 1 over 2i, 1 over 2i squared, and so forth. This is not quite a geometric series, but we can factor out 1 over 2i, and then what's left is a geometric series. We take our a equal 1 over 2i in the formula from theorem 134. And then we have this here, just writing this series in this format. And then we have 1 over 2i, and from our theorem 134, the sum is 1 over 1 minus 1 over 2i. We can get a common denominator here and then flip it like this. The 2i and 2i cancel. We get 1 over 2i minus 1, which we can leave it at that, but a lot of times you'll see textbooks will multiply by the conjugate of the denominator. So this is basically 1, but it changes the format. So on the bottom you get 5, and on the top you get the minus 1 minus 2i, and you get that as your solution. Similar to real valued series, we have the comparison test. Basically, if one series known to converge bounds another series after a certain number of terms and out to infinity, then the other series also converges. So just writing it out a little more formally here, if the modulus of a sub j is less than or equal to b sub j for all j greater than some n, and the real valued series, in other words, these b sub j's are real numbers, not complex, converges, then so does the complex series. So we have an example here. We'll take this series here, 3i plus I, 3i over 4 squared, and so forth. When you plug in j equals 0, 1, 2, and you have that series. So the question is, what do we compare this to? Well, we have a geometric series that is pretty similar, which I've drawn down here. So you have 3 times the series of 1 over 2 to the j, and that gives you a 3 over 2, 3 over 2 squared. So you notice here, these look pretty close, and this converges to 6. So we just need to show that after some index n, each term in this series is bigger than each one of these. So if we take the modulus, I should say the modulus of the terms in this series. So if we take the modulus of a general term here, we get 3, because the modulus of 1 is I is 1, over j plus 2 to the jth power. And that's less than or equal to 3 over just 2 to the j, which is our b to the j term. So that pretty much proves it. We have a convergence series, and we've shown the modulus of this, the terms of this series are less than the terms of the convergence series. Actually, for our n here is just 0 for every possible term, but it could have been, for another example, it could have been n equals 100. The main thing is after a certain index, everything in one series is bigger than the other. There's something called absolute convergence, and it's basically a series is said to absolutely converge if the modulus of the terms converges. And it follows from the comparison test that an absolutely convergent series is convergent. The converse is not true, and I give you an example here. If you take this complex series, I times minus 1 to the n over n, you can factor the I out, and we know from the alternating harmonic series in calculus that this is log 2. So this converges, this complex series converges, but if you take the modulus of these terms, you just get this, the harmonic series, and we know that diverges, so we have our counterexample. And just as a reference, if you've forgotten the harmonic series and the alternating harmonic series, there's a Wikipedia page on that, and I put the link here. You can just look up on the Wikipedia alternating series and you'll find some background information, but hopefully you remember this from calculus. We have the ratio test for complex series, which I'm going to show you here. So you have this series a sub j from 0 to infinity, and if the limit of the modulus of a sub j plus 1 over a sub j equals some value a, then the series converges if a is less than 1 and diverges if a is greater than 1, and there's no conclusion from the test if a equals 1. So we take the case when a is less than 1, we pick a real number r that's less than 1 but bigger than a. This implies that the modulus of a sub n plus 1 is less than r times the modulus of a sub n for all n greater than some sufficiently large capital N. And then we can just, if we take the modulus of a n plus j and then just repeatedly use this inequality here, we'll eventually get that it's less than r to the j modulus of a sub n for all n greater than some n and j greater than 0. And then we have this chain of inequalities here. So the tail of the series, we're going to show that that's bounded. It's less than infinity. And then, of course, the first part of the series is only n terms, so that would be a constant. And then putting those two things together would prove that the series itself converges. So we're rewriting this term here this way. It's the same thing. You notice if you put in j equals 1, you get n plus 1 and so forth. So these two are the same. But the reason I wrote it this way is then we can now use this inequality, plug that in. Now we're less than r to the j, the modulus of a sub n. We can factor out the a sub n since it doesn't involve the j. And then we know what this is. This is almost a geometric series for real numbers, And what we can do is we can just add one more term. That's why I put this in red here. We can add the term 1, r to the 0, 1. So this is less than that. And then we know what this is. It's r over 1 minus r. And so this whole thing here, it converges. It's less than infinity. And as I say, if the tail of the series is less than infinity and the first part of the series we know is a constant, then the entire series converges. So let's continue this on the next slide. In the case that a is greater than 1, we have that the modulus of the ratio a sub n plus 1 over a sub n is greater than 1 for all n greater than some capital N, and that implies that the modulus of a sub n plus k is greater than a sub n for all k greater than 1. Basically, the terms get larger at some point and going out to infinity. So that implies the limit as n approaches infinity of a sub n does not equal 0. And by contradiction to theorem 133, we have that our series diverges at the case that a is greater than 1. So we can take an example here, the sum from j equals 0 to infinity of 3i to the j over j factorial. We plug our terms into our ratio. You can see here that the j factorial and the j plus 1 factorial, you just left with the j plus 1. You can break out the 3 to the j plus 1 and the I to the j plus 1, as we have here, and noting that the modulus of a real number is just the number itself, so we get this here and here. The modulus of I to any power is just 1, so these go away, and then you have the 3 divided into the 3 to the j into the 3j plus 1. That leaves us with 3. We take our limit and plugging in the 3 over j plus 1, the limit as j goes to infinity is of this is 0, which is less than 1. So for the ratio test, this series converges. We can define convergence for a sequence of functions as follows. Let's take a sequence of functions here, f sub n of z, n equals 1 to infinity or 0 to infinity, whatever index you need. And for each value of n, you have a different function, and that's said to converge pointwise to a function f of z over a set s, if for every epsilon greater than 0, there exists an n which depends on epsilon and z, such that f of z minus f sub n of z is less than epsilon whenever n is greater than small n is greater than capital N for all z in some set S, in which case we write the limit as n approaches infinity of f sub n of z equals f of z over a set S for all z in S. So in this definition, the n depended on both the epsilon that we've selected and as well as the value of z. Now, if the n does not depend on the value of z, we have something called uniform convergence. So I write here, if n in our definition up here only depends on epsilon, then and the limit exists, and the function is said to converge uniformly. And we can also define the series of functions. So we have here the sum from j equals 0 to infinity of f sub j of z converges uniformly to some function f of z if the sequence of partial sums, when you're just going from j equals 0 to n of these functions, converges uniformly to f of z. And again, that would be over some set. It doesn't have to be the entire set of complex numbers. It could be a subset. So let's do an example of a series. We'll have the sum from j equals 0 to infinity of c times z to the j power, where c is some constant, a complex number. In the proof from theorem 134, we had this formula, which I want to reuse here. We'll let a equal cz in this formula. We plug that in, so nothing extraordinary here. We just have everywhere for a, we have cz. We'll call that equation 1. So when the modulus of c times z is less than 1, or equivalently when z, the modulus of z is greater than 1 over the modulus of c, then the series converges to 1 over 1 minus cz. So that's from a previous result. Continuing with our example, and recalling that in the last slide we showed regular convergence, now we're going to show that our series converges uniformly. So to prove that, consider a closed disk, modulus of z less than or equal to r. So a disk centered at the origin with radius less than or equal to r, for r less than 1 over the modulus of c. So from this assumption here, we have these three things. Let me explain them individually. So the first one is the modulus of cz to the n plus 1 is less than this expression here. And all we've done is take this part here, the modulus of z less than or equal to r, and we've replaced z with r. So we have this here. Then this one follows even more simply. We have the modulus of cz less than r modulus of c, which is less than 1. So the first part comes from here. And then the second inequality comes from just multiplying the c times the r. We get this here. Then this one here comes from the variation of the triangle inequality, which we did way back in one of the initial lessons. So 1 minus cz is greater than or equal to 1 minus the modulus of cz. And we've shown that this modulus is less than 1, so, and it's also less than r modulus of c. So we can replace this by this, and this will be bigger because this is a smaller number that we're subtracting from 1 than this number here. So given those three, what we can do is work on this modulus here. Now let me just remind you that we had this equation from the previous slide. I called it equation 1. So we want to show that this thing here is bounded and goes and can be made as small as we need to. So using these three inequalities, we can say that this modulus here is less than this. So let me take one bit at a time. So on the top, we're just replacing this with this. So you see that here. Then on the bottom, we're replacing this with this, since we're replacing something with a bigger number here that preserves the less than. And we can make this as small as we want, and therefore we can make this as small as we want, and therefore this eventually can be the limit of this eventually goes to 0, which means this term equals this term here as n goes to infinity, which is what we wanted to prove. So why can we make this as small as we want? Well, for a given n, taking of n sufficiently large, the denominator is a constant, and the numerator is, where are we here? This here, r modulus of c, is a number less than 1. So the bigger we make n, the smaller this gets, and it's divided by the same term below. So independent of z, you notice there's no z in this expression. So independent of z, for a given value of epsilon greater than 0, we can find n sufficiently large such that this quantity is less than epsilon, which, as I say, implies this is going to 0 as n goes to infinity, which implies this term equals this series as n goes to infinity, so an infinite number of terms. And that's what we wanted to prove, that we have uniform convergence of this function to this series here as n goes to infinity, independent of z, which is the meaning of the term uniform convergence. Okay, I have a couple of exercises for you to try. First one is the series from n equals 1 to infinity of 2 over n cubed minus I to the n. Show that that diverges. And my hint is to look at the pattern from the real and imaginary parts of the of this term. Second one is determine whether or not this series 1/2 plus I to the n, sum from n equals 1 to infinity, determine whether or not that converges. And my hint here is to look at the modulus of the 1/2 plus I. And when you compute that, you see that that's bigger than 1. Then the last one is the sum from n equals 1 to infinity of n times I to the n divided by 3n plus 1. Determine whether or not that converges. And as a hint, as n approaches infinity, this part of it, n over 3n plus 1 approaches 1/3, and I to the n alternates. We saw that before. That alternates between 4 different values. Okay, so that's the end of this lesson, and hopefully you'll gain some experience in looking at these and trying these exercises.